Hello, my name is Dr. Tamie Jovanelly, and I'm excited to be here with you today to talk about geology. As one of our very first class lectures, it makes sense that we start to talk about geologic time, because that's truly how geology is organized. And the beauty of the science is that we're looking at the age of our planet and how things have changed and evolved over the course of about 4.6 billion years. So we're dealing with this huge time frame, and in order to discuss it, we have to organize it. So we usually talk in terms of either relative time or absolute time. Absolute time will come later in the semester. Here we're going to focus on relative time. So by definition that you'll find on your screen, relative time is used when assigning approximate ages. So the idea is that you're looking at something in nature and trying to assign an approximate age to it. And relative time is really a foundational principle of geology. The first geology textbook wasn't written until 1865 by Chuck Lyell. And so they didn't have the technology to absolutely assign an age to a rock. They hadn't been invented yet and wouldn't be invented until 1950. So looking at things in some type of order gave geologists a clue as to what their age would be. So I want to give you an example of that using my big Italian family. So when we talk about relative time, we always list our ages oldest to youngest. So you're listing them in some sort of column where the oldest age will be on the bottom and the youngest age will be on the top. So if you're following along with me, you're going to write down Mr. Jovanelly at the bottom of your paper, and then on top you're going to write Mrs. Jovanelly. Then you're going to write my big brother Jim, my brother Tim, my sister Cindy, my sister Karen, and then I would be at the top, Tammy, and I'm the youngest of 5. So we've listed our column in order of oldest: mom, dad, dad, mom, Jim, Tim, Cindy, Karen, Tammy. And so without assigning ages to any of those, knowing that they're in some type of order, we can make some comparisons. So you can say Jim is older than Tim, Tammy is younger than Karen, Cindy is older than Karen, Dad is the oldest. So you're picking up what I'm throwing down. So it's just that they're listed in some type of order where we can make comparisons. So even you at home, you can look outside at the landscape and you can know that the youngest rocks are exposed at the Earth's surface, and then they will get consecutively older as you go down towards the center of the Earth. So it's a pretty useful tool, and we'll be using that tool throughout the semester. It is called stratigraphy when we're looking at the layering and organization of rocks. So that gives us some type of relative perspective. The other thing that we're trying to do in this class is get our mind around age and time and what that means. Because when we ask the question, how old is old, what do you really think about? So asking yourself, how old is old? What's the oldest thing that you can think about? Usually, when I ask that question in class, people put that in terms of human perspective. So we can think of Jimmy Carter. Some might say he is old. He's upwards of 90 years old, right? Human lifetime. Hopefully, you reach 100 years old, but really the mean age is about 78 in the United States. So age for our human lifetime maybe is 100 years old, and we can compare that to our youth. So here's a picture of my niece Allison. So if our human lifetime is only 100 years old, it makes it a little bit challenging to consider the science of geology, because we're trying to expand our mind to consider the age of the Earth being about 4.6 billion years. 4.6 billion years is the age of the Earth. And so even beyond our human lifetime, if we think of some of the oldest things on the planet, we can look at the redwoods. They're about 500 years old. Joshua trees in California can be thousands of years old, but it's just a very small snapshot of the age of the Earth, being 4.6 billion years old. So it's tricky, and it's one of the harder things to get our minds kind of wrapped around when we begin to study geology for the very first time. To help us to do that, we organize time from oldest to youngest, again, in a fashion of a column, by using a geologic time scale. So you'll see this on your first test and others that will come throughout the semester. So it's one of our very important tools that we use. And what the geologic time scale does is it organizes time into different sections. So our largest section of time is called an eon. That's followed by a geologic era, a geologic period, and a geologic epoch. So the largest unit of time is an eon. The smallest unit of time is an epoch. So looking at our geologic time scale and now understanding that the oldest unit is going to be at the bottom, you can identify the PreCambrian. So the PreCambrian is an eon, and that PreCambrian eon starts at 4.6 billion years and goes all the way to about 570 million years. So write that down. The PreCambrian eon extends from 4.6 billion years to about 570 million years. So that unit of time represents about 80% of all geologic time. The PreCambrian represents 80% of all geologic time. That'll be a test question. So my question to you then is, why isn't the PreCambrian separated into smaller parts? So if you look at the remainder of the geologic timetable, you notice that there's geologic eras and there's periods and there's geologic epochs, but the PreCambrian, representing 80% of all geologic time, is only an eon. So I'll let you think about that for a second. And I'm wondering what you're coming up with. So honestly, when we describe the PreCambrian, there's not a whole lot going on. So about halfway through, we see the uprising of simple-celled organisms called cyanobacteria, which is going to be very important to climate change. It's because it's going to cool the climate and help to create our atmosphere. But other than that, we don't see a whole lot of things in the fossil record. Additionally, because of a process that's called plate tectonics, which we'll study in this class, you have plates that are moving throughout the globe over geologic time. So you have crust that's being created and you have crust that's being destroyed. And so a lot of that PreCambrian record doesn't exist anymore. So we're lucky enough to find portions of it at the bottom of the Grand Canyon, up in the Upper Peninsula of Michigan, in Australia, in some places in Greenland. But a lot of the geologic record of the PreCambrian has been just completely destroyed by the processes of plate tectonics. And if it does still remain, then a lot of it has been buried. So you have crust that's continually made over the course of these billions of years. And so the PreCambrian crust can be, in some places, very deep. So it might still exist, but we just can't get at it. So not a whole lot going on, not a whole lot of PreCambrian crust that's left, or it's too deep to get to. So that's the reasons why we don't separate the PreCambrian into smaller and smaller parts. But when we move forward 570 million years to modern day, we do separate the remainder first into geologic eras. And with our geologic eras, you notice starting at 570 million years, you have the Paleozoic. Paleozoic ends at about 248. Then you start the Mesozoic. The Mesozoic goes from about 248 million years to about 66 million years. And then at 66 million years, you move into the Cenozoic era, where we are currently at today. So there are three different geologic eras. So my next question for the audience at home is, what separates the geologic eras? So you'll notice that they're not separated by equal time. So the Paleozoic is much longer than the Mesozoic. And what I just said was that the Cenozoic is still ongoing. So we haven't yet ended the Cenozoic. So looking at the geologic timetable, something might cue you in that you might be aware of. And thinking in terms of the Mesozoic and how the Mesozoic era ended with the extinction of the dinosaurs. So geologic eras end in mass extinction. So the Paleozoic ends at 248 million years with a mass extinction. The Mesozoic ends at 66 million years with a mass extinction. And the Cenozoic ends, no, maybe, I don't know, maybe it will end in a mass extinction. That's to be continued, right? So when in geology we talk about mass extinction, we are saying that at least 70% of life on the planet dies. Write that down. A mass extinction is defined by 70% of all life on the planet kicking the bucket. So there's a pretty significant mass extinction at the end of the Paleozoic, obviously. And then we also see the extinction of the dinosaurs at 66 million years ago. There have been other mass extinctions, but those were the ones that were considered to be revolutionary enough to throw us into a different unit of geologic time. Okay, so we have geologic eons, eras, and then geologic periods. And you notice that there are several of these. So on your first exam, what you're going to receive is a blank geologic timetable. And I'm going to ask you to fill in the geologic eras and the geologic periods. You don't have to know the time for the first exam, but you have to know the Paleozoic, Mesozoic, and Cenozoic, and then you have to know the geologic periods. So how you're going to remember this is by a mnemonic, remembering that the oldest unit of time is at the bottom, the youngest is at the top, and you're going to write down, come over someday, maybe play poker, 3 jacks can take queen. There's other mnemonics, or you can make your own. This is just a way we're going to organize the geologic period so that you can remember them. So just to repeat that, come over someday, maybe play poker, 3 jacks can take queen. So that helps you to organize the Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous, Tertiary, and then the Quaternary, from oldest to youngest. So those geologic periods represent the past 570 million years. My question for you then is, why do we separate geologic eras into geologic periods? And when looking at this particular geologic timetable, you can tell that each of those different geologic periods represents a different unit of life, or different change or uprising of life. So like when we talk about the Devonian, for example, the Devonian is known as the age of fishes. And you can see a variety of different uprisings of life that we can focus on throughout this semester. So we very much rely on the fossil record to give us those descriptions of those different geologic periods. And what we're going to learn is that the past environments are going to have a whole lot to do with the changes of life that we see on the planet, and the position of the continents. So as the plates are moving about the globe closer to the equator and farther away from the equator, there's going to be changes in life and the amount of diversity that we see over time. So, so geologic periods, and then you'll notice that the Cenozoic is broken up into smaller units beyond the geologic period. So those are broken up into epochs. So for all the opposite reasons of why we don't break up the PreCambrian into smaller units of time, that is exactly why we do break up the Cenozoic into these geologic epochs even. So the units are obviously closer to the Earth's surface, so we're able to explore them pretty readily. There is a whole lot of changes that occur. Most of the changes here happen because of climate change. So we can look at those climate change patterns in a much smaller unit of time because there is the availability of being able to study them because they're close enough to the Earth's surface. So we know an awful lot about changes of life on the planet over the past 66 million years as a result of that. So moving into the Cenozoic, which is also called the age of mammals. Other things to keep in mind when we look at the geologic timetable, when we talk about the Precambrian eon can also be called the Cryptozoic eon. So if you're reading in your lab manual or the textbook, Precambrian is sometimes referred to as the Cryptozoic eon. Also, if we're referring to the past 570 million years, that can be referred to as the Phanerozoic eon. So lumping that entire unit of time together is called the Phanerozoic eon. What you'll notice on here is that we can look in terms of units for millions of years. So MYA is millions of years ago. MYO is millions of years old. MY is just millions of years. Sometimes the unit of GA, a giga, is referred to as a billion years. So just kind of look for those terms and units as we move forward in time. Recognize that 4,600 million years is the same thing as saying 4.6 billion years. It's just a conversion. So you'll see all of this on exam 1. So let's practice. Let's do some practicing. First question, what geologic time frame do we live in? Looking at your geologic timetable, how would you answer that question? What geologic time frame do we live in? And so it's a little bit of a trick question because it depends on how detailed we want to be when we answer. So the first thing we could say is we live in the Cenozoic, we live in the Quaternary period, or we could say that we live in the Holocene epoch. And truly, another geologic epoch has been added. It's called the Anthropocene. And so the Anthropocene follows the Holocene because remember when we talk about geologic epochs, these are separated based on climate change. And so the Anthropocene is really the Geological Society of America recognizing that the climate is changing and it's changing due to anthropogenic sources. So by us adding carbon dioxide, humans, into the atmosphere, the climate has changed. So that's a little bit of a modern update. So we could also ask the question, how would one refer to modern time? And usually modern time, we talk about the Anthropocene or the Holocene. So the past like 10,000 years is considered to be the modern time, our modern geological record. And our last question, what era did the dinosaurs live? And we all know and love the movie Jurassic Park, and the Jurassic Park is a geologic period that was in the Mesozoic. So the Mesozoic is known as the age of reptiles. Another thing to point out about the geologic time scale in relating to these geologic eras, the Paleozoic, Mesozoic, and Cenozoic. Paleo means ancient, Meso means middle, and Ceno means early time. So those are the prefixes that help you to organize those as you're preparing for your first test. Okay, so I also want to talk about some perspectives about geologic time as we try to get our mind around the idea of age and change. And so I present you with, if the cat is white, does that mean the cat has never been pink? If the cat is white, does that mean that the cat has never been pink? And so this ties into an idea that's called the principle of geologic gap. And a lot of what we're going to be seeing in here when we're talking about geologic time relates directly to how it has been extracted from the fossil record. So the idea is when we look at geologic time, and one of the things that makes geology so exciting is that we are constantly putting pieces of the puzzle together still. So if the cat is white, does that mean the cat has ever been pink? It's like the idea that you find a fossil and you can't make assumptions that there's never been, you find the cat that's white, you can't make the assumption that the cat has never been pink just because you haven't found it yet. Here's a real example. So what you've all grown up with is the idea that T-Rex is the baddest and most savage land-based reptile ever, right? And so you've been to all the natural history museums and you've seen this ginormous reptile towering over everything else. And so for a very long time, really up until about 2019, it was thought that T-Rex was, in fact, one of the largest predators on the planet until the Gigantosaurus was found. So if the cat is white, does that mean the cat has never been pink? We filled in part of the geologic record by finding something that was bigger. And that's what's truly fascinating, again, about geology, is that we're constantly finding things that challenge is the way we used to think. And there's been some very major, pieces of the puzzles that have been filled in over geologic time that gives us ideas of the evolution of life on the planet. And we'll talk about some of those examples as we get to them in class. So the principle of geologic gap. And then the next is the principle of geologic boundary. So we're always up against geologic boundaries because we're up against the maximum capacity of which our technology can push us forward. So we've already mentioned one of those geologic boundaries, and that was when Chuck Lyell was writing his Principles of Geology in 1865. Everything he talked about was relative time, so just putting things into sequence. And that was because it wasn't until 1950 that the technology was invented where we could, specifically a mass spectrometer was invented, where we could absolutely date rocks and assign ages. So the mass spectrometer had to be invented first before we could assign ages. And once that happened, it threw us forward in the science, and we were able to quickly advance. Another thing that happened relatively recently was biologists, science wanted to explore the Marianas Trench. So the Marianas Trench is off of Japan. It is the deepest part of the ocean. It's as deep as Mount Everest is tall. So it's over 28,000 feet deep. And so there wasn't any technology where we could explore the depths of that trench until a fellow by the name of James Cameron, which some of you might know because he's the fellow that put together the Avatar movie. So he is independently wealthy, and he decided that he wanted to build a submersible that would go to the bottom of the trench. And so he did. And so in 2012, the submersible that was built for him, he took it to the very bottom of the trench. He was not there for very long, but by his initiation of building something that took us to the bottom of the trench, we had overcome a geologic boundary that we had never been to before. So we're able to collect all these different types of data through his submersible that is still being processed. And so now we have an understanding of what life looks like at the bottom of the trench. So overcoming geologic boundaries helps our science to move forward. And there's many geological boundaries that we're up against still, and we'll talk about some of those throughout the class. So just to review, the purpose of what we're going to do is we're really going to utilize the geologic timetable as one of our greatest tools to explore the age of the earth, the uprising of life, how plates are moving about the globe, and how all of this is going to impact climate change. And so that's where we're going to be moving forward to in the next 16 weeks or so. So go ahead and get your mind around the geologic timescale. I've uploaded this onto the website platforms so that you can begin to study for exam 1. Remembering that you're going to have to know the eras and the geologic periods in order. You do not need to know the dates. So I think I'm going to stop here for today. You've been a wonderful audience, and I will talk to you soon.